22 students here. How many? I mean, this is a elective paper. Has all of you opted for this?
Yes, sir, because no other paper was offered anyways.
Okay. So the number of students should be much higher than this, right? More than 35 or something, like?
Yes, sir. Generally it is.
Okay. So who are the ones today? It's Anik Haldar, Aniruddha, Chirantan, Devangana. But actually I received the accepted that message from a lot many. So alphabetically, could you please turn on your video just for a few seconds? As I see, Ognisha Bhomik, could you please turn on your video?
Yes, sir.
Okay, fine, thanks. Then Anik Haldar, okay. Aniruddha Mondol, okay. Chirantan Ganguly, okay. Okay, fine. So let's begin now. So I think in the last class we had talked up to, I think, the Doppler shift, okay, and the eclipse of the satellite, right? And we also did some small problems on calculation of the Doppler shift. So what we understood is that the Doppler shift, this is a phenomena which with which we were familiar mostly uh, based on acoustic signals. Like, we were given that example that when a train approaches a station and is blowing its horn, then you hear a different kind of a sound than when the train is receding or moving away from the station and it is still blowing the horn. So we were more familiar with that kind of an example, but now we realize that Doppler shift is not a phenomena which is exclusive for acoustic signals only. It's a general property of all electromagnetic signals, and hence radio signals also are subject to Doppler shift. And this, since this arises out of the relative motion between the transmitter and the receiver, so it is expected to be quite pronounced for the low Earth orbiting satellites because the orbital velocities are quite high, comparatively high for the low Earth orbiting satellites than the medium Earth orbiting or the geostationary satellites. And so, in case of low Earth orbiting satellite receiving systems, the bandwidth of the receiver becomes an issue or becomes a criteria, particularly when the Doppler shift exceeds a certain value and you are using some kind of a narrowband receiver, right? Because then the after suffering Doppler shift, the transmitted signal which we are trying to receive, that may suffer a frequency deviation which may push it, beyond the bandwidth of the narrowband receiver. So Some compensation techniques are necessary in that case for frequency, for tracking that particular frequency signal. And then for about the eclipse of the satellite, we had seen that that kind of a scenario happens only when the sun, earth, and the satellite, they all lie along the same, they lie in the same plane along the same line. So under that kind of a situation, you have the earth blocking the direct solar radiation from reaching the satellite. Now, because in case of a satellite, whatever may be the category of that satellite, whether low Earth orbiting, medium Earth orbiting, or geostationary, so because the primary source of energy on board a satellite are the solar radiation, are the solar energy converted to electrical energy. So, during this period of time, which may last even up to say 70 minutes or so, in the as we approach the day of the equinox. Why equinox? Because that is the period of time when actually this kind of a geometrical configuration is satisfied. That is, you have the sun, earth, and the satellite all lying in the same plane and along the same line. Okay. So, under this kind of a situation, that is when the equinoxes happen, once during March and the other around September. So, this being a natural phenomena, we cannot, kind of eliminate this effect. So, the harmful results that we often find in case of this eclipse of the satellite is that this produces harmful transients near the beginning and the end of an eclipse, because as we can understand that the outer surface of a satellite, that is receiving close to about 1400 watts of power from the sun per square meter. It's a huge amount of power. 1.4 kilowatt per square meter of solar radiation is incident. So that heats up the outer surface of the satellite to a great extent. And uh, when it passes into the shadow of the earth, there is a huge temperature fall. That means the temperature gradient is very large, and you have in the shadow of the earth temperatures reaching near to absolute zero. That means like close to minus 200 degrees Celsius even. So while it is exposed to the direct sunlight, as in the situation like here, when the satellite is here, it is receiving direct radiation from the sun, or even there or anywhere else. So at that time, because of the huge amount of solar radiation being incident on the satellite, it causes the outside surface of the satellite to have temperatures which are in excess of maybe 150 to 200 degrees Celsius. And from there, within a few minutes, the temperature falls close to absolute zero. So this puts a huge thermal stress on the satellite, and most of the satellite failures, they occur around this time. Also, the solar radiation being the primary source of power for the satellites, any kind of satellite, this being cut off, it results in majority of the communication subsystems or other subsystems being turned off for that period of time. And that period or that interval may extend from about 10 minutes to a maximum of say 70 minutes. Okay. And under that kind of a situation, earlier in the 1980s also, perhaps none of you were born at that time. So at that time, what happened was that the National Network Program of Doordarshan, because in the 1980s, around 1987, 88, around that time, the DTH or the cable channels were not there. So at that time, the Indian national satellite INSAT used to transmit the Doordarshan national programs. So we used to find at that time that during this period of the two equinoxes, that means for about 1.5 months around each equinox, it's roughly 23 plus 23, 46 days. So that's close to 1.5 months. So for 1.5 months around the equinoxes, the transmission of the national program was stopped because the satellites in those days they did not have the the adequate technology to deal with that kind of a situation that requires that you need to have very high backup power sources on board the satellite. Okay, naturally the question might come that okay, why don't we put battery after battery, many number of batteries in the satellite, and like we have these high capacity UPS nowadays. So why don't we do that? The answer to that lies in the fact that as we increase the load of the satellite, the weight of the satellite, then there is a corresponding increase in the cost of launch of the satellite as well. Because as we will understand that even today, putting 1 kg of any object at geostationary orbit, this costs something in excess of 1 million US dollar. Okay, 1 million US dollar. So that's like about 10 lakh US dollar. So that's like 10 lakh into say 74 or 75 if you want to convert that to Indian rupees. So how much will that be? About I think 750 lakh Indian rupees. So that's about 7.5 crores. So the cost of putting 1 kg of any object or matter at geostationary orbit, that costs nowadays something to the tune of about 6 to 7 crores in terms of Indian rupees. So we can understand very well that there has to be a very critical assessment of what actually has to be put on board the satellite. So that's why nowadays there are globally efforts to use cube satellites or nano satellites, okay, uh, which are very small, maybe less than about 25 to 30 kgs. And the beauty of that is that nowadays there is a global, kind of movement where students at the even at the undergraduate level are designing this kind of a satellite. And uh, 2 years back, two of my BTech project students, they actually I sent them to Indian Institute of Space Science and Technology (IIST) at Trivandrum, where they have a division which actually kind of manufactures and assembles nano satellites or cube satellites. So they had a good experience there, they had a good training there for a few months. But then unfortunately just before this um, outbreak of the corona last year, they had to cut short their visit and return. I think they returned maybe around the middle of March, just about that time. So, what I want to stress is that nowadays, instead of having very big satellites, communication satellites, there is slowly a trend to test. To test, first of all. We cannot just simply put it into service right now because there has to be a lot of tests and checks to see and compare the performance of the small satellites with respect to the conventional large geostationary communication satellites, which could weigh a few thousands of kgs. So the idea is that this kind of a small, low power and small form, that means small size, satellites could also effectively be used for the purpose of this kind of a communication purpose. But of course, because these satellites, they will not be in geostationary orbit, but in low Earth orbit. So you need to have a constellation of those satellites. Okay. So this miniaturization of technology, uh, that happens also in case of satellites. It is not only limited to the domain of electronic chips and components, but nowadays satellites also, they are getting smaller ones into nanosats or cubesats. Now the next phenomena that we would like to discuss is what is known as the variation of the range of a satellite. Remember, these effects, all of these that we are discussing, these are some kind of observed phenomena when we try to communicate with the satellite, whether it is the Doppler shift, whether it is the eclipse of the satellite, or this particular effect which is known as the variation of the range or range variation. So the idea is that we had in some of the earlier classes shown a slide where we have seen a very congested space environment surrounding Earth, large number of satellites, I mean thousands and thousands of satellites. So, because of the large number of geostationary satellites nowadays in orbit, there is an international agreement that every country has to limit the movement of those satellites, because you see, theoretically, a geostationary satellite is fixed at a particular point. But from the practical point of view, we know that because of the various perturbations on a geostationary satellite in orbit, like arising from the non-spherical shape of Earth or from the gravitational attraction of other heavenly bodies, because of those, there is a tendency to move uh, within a certain limit. So it is the responsibility of the country which launches that satellite that they should restrict the movement of the geostationary satellites, because that position change, if it exceeds a certain value, it may collide with another nearby satellite. Right now, believe it or not, the separation between two geostationary satellites at their orbit is about 1 degree, just 1 degree separation. Okay, so this may seem unbelievable to you, but try to think that this is 1 degree at geostationary orbital altitude. Okay, so uh, that means that effectively we may be talking about uh, distance. If we try to calculate the distance at that height, it will be something like with respect to the center of the earth, say about 42,000 kilometer. Okay, uh, into this 1 degree, say. So it will be something like your 42,000 kilometer separation. Did you get this calculation? I'm just trying to use this S equals
Yes,
to
sir.
r theta, and so that tells us that this is the kind of separation, but from the perspective of the Earth, that is, when pointing your antenna towards the satellite, you can understand and appreciate the fact that it has to be very sharp and very pinpointed. Okay. Otherwise, instead of pointing towards a desired satellite, your antenna may be pointing towards some other satellite. So nowadays there is an international convention, or what I should say, regulation, that the movement of a geostationary satellite has to be limited within a cube, which is like zero point 0.5 degree on either side. That means whether in the three directions, because in space actually, up and down, these conventions, that is upward movement or downward movement, that does not make any sense in space. So we should say that in either of the three axial directions, the movement of the satellite should be limited to within 0.5 degree. Okay. Later on in the course, when we will talk a little bit about the multiple access techniques as used in case of satellite communication, then we will understand that even this, zero point 0.5 degree, zero point 0.5 degree means, following this calculation, it will be something like 21,000 kilometers, roughly. So this round trip signal propagation time, that will change, because if a satellite has moved, say, to zero point 0.5 degree on either side, or maybe 0.3 degree or whatever, associated with that, the distance also changes. Okay, that means the total round trip propagation time, that means a signal is transmitted from an earth station, is received by the satellite, and then retransmitted back to another user. So this entire round trip propagation distance will change, and correspondingly the time will change. Now, naturally, the question may arise that how much will be the time difference? Okay, so let us say that corresponding to a 21,000 kilometer uplink and a 21,000 kilometer downlink. Okay, so that means a signal is transmitted from an earth station, and the time that elapses is something like, say, it will be 21,000 into 2, and that should be divided by the free space velocity of light. So can you please tell me what will be the value of this time interval? This is in kilometer, okay? So you have to convert that to meters per second if you are using a value of c in meters per second. This 21,000 is in kilometers. Why 21,000? Because we have shown that it is 0.5 degree on either side.
So 0.14 second.
0.14 second. Okay, so let us just change this a little bit. Suppose the orbital altitude, the range of a satellite is typically, say, 42,000 kilometers from the center of the Earth. Okay, and about 36,000 kilometers from the surface of the Earth. So this 36,000 kilometer, you remember perhaps from some of the first classes, that this is the nominal orbital altitude. That is when the satellite is vertically overhead your location. But the communication satellites are never overhead, as we will see later on, but they are always in an off zenith direction. But even if we assume the ideal situation that they are roughly overhead your location, so that will be, the distance will be like 36,000 kilometers from the Earth station and 36,000 kilometers from the satellite to the receiver. So for this, what will be the amount of time taken?
0.24 second.
0.24 second. Is this calculation right? Is it correct?
Yes, sir.
Yes.
0.2%.
Because there's 42,000 into 2 into 1,000, because you are converting this to meters per second, by 3, and then there will be 10 to the power 8, right? So it will be like 0.24 or 0.28 seconds. So we can understand that within not even a second, but a fraction of a second, the satellite signal that will be that will cover the distance from the Earth station to the satellite and back to the and retransmitted to the user. So if there is a change in this, there will be a if there is a change in the distance of the satellite because it has moved to either one of the sites, then there will be a corresponding change in the total round trip distance, that is from the Earth station to the satellite and back to the user or receiver. So when that changes, there will be a corresponding change in this total signal round trip propagation time. So this range variation is extremely important, and in order to keep this within reasonable limits, by reasonable we mean that according to international convention, it has to be like zero 0.5 degree on either side, within a cube of 0.5 degree on either side. And a term which has now come into use associated with the communication satellites as well as navigation satellites is that station keeping. Okay, that means the ground control station that should be well equipped so as to monitor and take necessary action in case a satellite or any of its subsystems, they are not functioning properly at a period of time. And this station keeping, this is a term something like similar similar in meaning to housekeeping, like in the hospitality industry, in hotels like that, you have a separate department which looks after that the rooms are cleaned and all these things are in place. So just like that, in case of a satellite also, the ground station, it is the duty of the ground station, the responsibility of the ground station to check that every subsystem within the satellite is functioning properly. And then, of course, the natural question will be, how do they do that? Do they send up service people up there? No, that's not possible. That option is not there. So that means that there has to be some sensors placed associated with the various subsystems of the satellite. We will talk about that in details when we consider the different subsystems of a satellite. So this range variation is the third effect. And fourth is this sun transit outage. That means every day during certain period of time, which could be like say from 5 to 10 minutes or so, the sun that will pass directly in front of the within the primary beam of an antenna. I hope that by now in your last third semester, I think you had this antenna, or fourth semester you have the antenna and radio wave propagation, right? Some of you, not all of you. So there you might have known that what is meant by the primary beam of an antenna. Am I correct?
Yes, sir.
Yes. So
Yes, sir.
during certain period of the time, the sun that will pass through the primary beam. Just try to visualize this situation that suppose at certain point of the day, say early in the morning, when you look up in the sky, look up at the sky, the sun is on at near one of the horizon. And as the day progresses and as it approaches, say, noon time, the sun is gradually overhead. And at some point of the time, as you look up, the sun may directly pass through, the line joining you and the sun. So at that time, that is why it becomes difficult and is not advisable to look at the sun. So that is why that similar kind of a situation also happens in case of a earth station antenna. That is, at certain periods of time, the sun may pass directly through the primary beam of an earth station antenna. And the sun being, a source of noise and radiation at different wavelengths, including microwave wavelengths, microwave bands. So that will suddenly cause an increase in the signal to that will cause an increase in the noise associated with that particular signal, and the signal to noise ratio that will degrade, that will fall. So at those times, usually, either the traffic from this particular satellite, as is shown here, the by traffic we mean the communication data which is being transmitted through this satellite. So this is either offloaded to another satellite which is not yet in the sun transit position, or maybe over here for that brief interval of time. The other option is that you simply turn off your system at those times, but that is not also possible because you see during the daytime there is a lot of traffic, particularly around the noon time, and so you being the commercial interests are also there, and you cannot simply say to your user that okay fine, we will switch it off for 10 or 15 minutes now. That is not possible. That's a not possible solution in these days. So uh, that is another effect. And as I was mentioning, that the sun transit outage, it causes a significant increase in the overall receiver noise level. And this can disrupt the domestic data users also, as it occurs during the daytime, but not the international data users, because you see, like nowadays, majority of the traffic from India to the Western world, USA, is during the Indian night time. Okay, when it is daytime over there. So the international users are not so much affected by this phenomena, but the domestic users, like those in the Indian subcontinent or in the Asian sector, so to say, where we have nearly close, time zones. So here actually the effect is more felt of this the effect of the sun transit outage. So this is just another, picture of the large number of civilian aircraft. This is only for the civilian aircraft. There are also military spacecraft at geostationary orbits. So it's a very congested one. The earlier picture that we had seen, that was mainly for all the satellites, all the different categories of satellites combined together. And this space asset, this is roughly estimated to be greater than $200 billion. And I can tell you that this value is like 5 years back. So it has now grown many times, this $200 billion in space assets. And so there are several, measures taken in order to protect these kind of uh, infrastructure, and associated with the electrostatic discharge, sometimes on board the satellite a lot of damages happen. And this is just one picture from JPL, the Jet Propulsion Laboratory, where you can see that one of the onboard capacitors in a satellite system, that when you blow it up, when you highlight it or zoom that, you can actually identify the amount of damage which is caused by that electrostatic discharge. And there are, several kinds of space environment issues which are natural, like those arising from, what is known as the space weather. It is different from the terrestrial weather, like we are experiencing very heavy rainfall in Kolkata for the past few days. So that is like terrestrial weather. And the origin of this terrestrial weather is mainly, limited to within the first 8 to 10 kilometers from the surface of the Earth. That means you have all the atmospheric phenomena like rain or storm, or in some of the other countries, snow. All these systems are being generated within the first 8 to 10 kilometers from the surface of the Earth. And beyond that, that is like terrestrial weather. And beyond that, In the ionized part of the atmosphere, which roughly starts around 50 to 60 kilometer, there you have the phenomena which are, much more disruptive in nature. Like, in some of the cases, the solar radiation, they are highly energetic and they could cause the power grids in some of the countries in the high latitudes, not so much in the equatorial region, but in the high latitudes, they could cause the power grids to trip because suddenly these highly energetic particles emitted from the sun, they carry with it electric field and an associated, and when they couple with the Earth's geomagnetic field, they could induce huge amount of current in the power grids, like a million of amperes, 1 million amperes. So that's something with which the power grids are not designed for to handle. So that kind of a situation does happen, and uh, in some of the high latitude countries, where the heating, the room heating is very much needed, without which people cannot survive. So that happened sometime in August 2003. That large part of the northern part of US and Canada went without power for some days, and that resulted in the loss of human lives there. But that kind of a phenomena does not happen in the equatorial countries like India, or if you go to the other side of the earth, Brazil or South American countries. And uh, as I was telling you, just kind of a information for you that there are several kinds of phenomena which does affect satellite communication. Okay, and uh, some of which we have just got an idea, and then associated with these solar storms, there was a more recent event in 2015 when suddenly the entire Swedish airspace had to be closed down because the radars which track the aircrafts, they suddenly started malfunctioning, and there was a, because of a radio burst from the sun which happened there, and which happened and affected them. So at that time, none of the systems which helped the aircrafts to land, they worked, and as a result, what happened was that suddenly the airplanes and the entire Swedish air space was had to be shut down for several hours. And nowadays, as I was mentioning, that by satellite communication, we do not only mean satellites which are uh, confined within the first, say, 40,000 kilometer above the surface of the Earth, but even beyond that, there is a much greater amount of space which humans are now exploring. And for those satellites also, you need to have reliable and stable communication systems. Like as you can see, this ACE, Atmospheric Composition Explorer, this is a satellite which is way beyond our solar system, and some of them are also stationed about a few million kilometers from the surface of the Earth, so that they could actually, receive better information about the sun from the sun. Anyway, uh, this is just one video that I have over here. So let us see if this plays or not, about ISRO satellite launch. Can you hear the sound?
Sir, actually, as long as you not change the presentation format to share a tab, we cannot hear it. If you share
Share.
this, yes, sir,
Okay, okay. Share,
share tab.
share what?
Share tab. You will see an option while sharing.
Okay,
Stop.
so let us stop presenting, and then present a window or what?
Yeah, a tab. So the last one, best for
It's
video and
window.
animation. So below that, is there anything written?
No, no, no. It's only your entire screen or a window.
Sir, probably you can try opening the YouTube link in your Chrome or the browser that you're using.
Yes.
If you can copy that and put it there.
Okay. Let me see. And now I should share my screen, right?
Sir, now you can see a tab option like below the window. Is there option of sharing a tab?
No, no.
Okay, so then maybe we can try sharing a window and probably after that we can hear.
Okay. So let's see. So can you hear now?
No, sir. Oh, okay, sir. We can hear it now.
Okay.
April the 18th, 2001 is a great day on which the decade-long efforts of the Indian Space Research Organization, ISRO, were put to the severe and ultimate test. Yes, it was the day on which the first developmental flight of the Geosynchronous Satellite Launch Vehicle, GSLV in short, took place from the
Present, sir.
Sir, 313 present.
Okay. 315. 316.
Present, sir.
317. 318. 319. 320.
Present, sir.
321.
Present, sir.
322. 323.
Present, sir.
401.
Present, sir.
401.
Present, sir.
Okay. 402.
Yes, sir.
405. 407. 408.
Present, sir.
411.
Present, sir.
414.
Present, sir.
420.
Present, sir.
421.
Present, sir.
422. 423.
Present, sir.
424.
Present, sir.
430.
Yes, sir. Present, sir.
431.
Yes, sir.
432.
Yes, sir.
433. 435. 436. 437.
Present, sir.
438.
Present, sir.
439.
Yes, sir.
440.
Yes, sir.
441. 442.
Yes, sir.
Shayan Datta.
Present, sir. Present.
Ravi Kumar Thakur. Okay. Thank you.
Thank you.